I am Juan Quintela, I work for Red Hat, and we are going to talk about migration 1 year later. I gave a similar talk last KVM Forum, and the sad news, we are more or less with the same problems than last year, but we know more problems that we didn't know last year. It's just incredible. Well, I am going to state what is the current state of migration just now, what are the current problems that we know, some of the ideas that we have in the things to do, and some solutions, some problems that we were discussing in the mailing list lately. Okay, the first, what needs to be moved? When we are doing migration, we need to move the state of one machine to another machine. One of the things that we need to move is memory. The problem with memory is that it is big, and each time is bigger. We have just now a lot of customers using 8 gigabytes guest, and partners are asking for so much memory. If you think about it, moving so much memory from one machine to other is going to be slow. It doesn't matter how we do it. You thought that memory was big. Think about disk. We have had the 2 previous talks about disk. Basically, in disk, we are talking about terabytes. We also want to move from one stage to other. And then, one machine is also composed of several devices. The advantage of the devices is that size is really small. Really, in a normal configuration, the size of the devices is something in the order of 2-3 megabytes of state. That means it didn't matter. That means that we are cheating. Moving the 2-3 things is what we call the live migration. That is the difficult thing at the device. We just sent the state at the end. Okay. When we talk about migration, one of the things that we are talking always is compatibility between backward compatibility and forward compatibility. Normally, old to old, old version to old version, or new version to new version should be no problem. Okay, normally it works, but sometimes it don't work. Then we have old to new versions. Old to new version is that we have an old version of QEMU running, and we want to be able to migrate to a new version of QEMU. Basically, that works. Why? Because the new version is the future. We know what things have changed. Then, normally it works. The problem is that sometimes we went the other way around. That is, for a new version, going to old version. What did happen? This happens basically when you have a lot of machines, a lot of servers. You don't want to have to migrate all the machines at the same time to the same version. Okay. That was some of the problems. We can continue. When we are talking about that, we talk about sections, subsections, version. What is that? Okay, sections. Each device has some state. That is one section. Easy. Subsection. There are some states that can be there or cannot be there, can be needed or cannot be needed. That is what it is represented. This is basically the only way that we have to send partial state to other machine. It's the source who decides if it is sent or not. And now what is versions? Okay, one device can change its state for one place, for one version to other. If it changes its state, we need to change the sections, the version of the section. To make things more interesting, we decided last year to try never to change again one device section. Why? Because in the moment that we change one section, it's impossible to do one backward compatibility migration. Then we try to do everything with subsections. Basically, this is one of the few things that we did relatively well, in the sense that in everything that we have changed in 1 year, only one change or 2 have not been able to be represented correctly with subsection. We were quite well there. Well, subsections supposes that we'll finish every problem that we have with migration. They help it, but just before, basically the idea is the source, when they need to send some state that is optional, it just tests if that state is necessary. Normally the source no, and if it is not necessary, it is not sent. Why is this important? Well, normally when we have one device, And migration works is because we have every state that we need. The problem is that sometimes we are in the middle of some strange operation that needs some more state. Notice that if that state were always needed, migration would have never worked. What is it? Well, for instance, one of the examples was IDE-PO operations. What happened here? That happens that only are needed in the middle of one PIO operations. Basically, you are running, for instance, Linux, PIO is only used during boot. That means that if you migrate in any other moment, there is no problem. This worked more or less. It worked well in the sense that we were able to fix every problem. The problem with suggestions is that we are not able to detect if we are in a suggestion or not. Well, another thing, we are going to describe how works line migration. Line migration is that once that we have more memory, waiting through while all the memory is transferred takes too much time. So we try to continue running the GAST while we are migrating memory. As you can guess, that makes some kind of problems. As we are doing, memory is big. That takes quite a bit. The problem is if we fail in the mail-out operation. We have memory corruption and normally the machine crash or worse thing happens. With disk, it's still worse because if we fail in the middle of one disk migration, we lost data and basically nobody likes that. Well, now once that we are here, we have already have two talks about this migration, and basically, if you look for far away, this is exactly the same problem. The only problem is that this is bigger. So we are leaving that there. Well, now we are going to describe line migration, how it works. Okay, we have memory, and we have one bitmap indicating if each page is dirty or not. If it is, if guest has right there. So when we start line migration, we just mark every page is dirty. Now we loop through the bitmap, one time, another time. And for each page, we copy the page to the destination, we clear the bit, and we repeat until when? We repeat until in the loop there is a low enough number of pages. At that point, we just stop the guest, we transfer the rest of the pages and the devices, and we continue in the destinations. And that is basically what we call migration, how line migration works. To make things more interesting, we call that stages. And we call it stage 1 is what I marked with E, A. Stage 2B is basically when we send the memory one around this loop, and stage 3 is when we resend the rest of the thing. As we need to overload things in QEMU, stage -1 means we have one error. Well, now the other thing is how QEMU works. This was a surprise for me when I see it the first time. Basically, we have a main loop, and the main loop is something like that. We have one while, we unlock one thread, we do one select, and we look one thread again. And that is it. Remember this comment? We will refer to code that is there later. And what does each BCPU? Each BCPU is basically the same. One loop, it unlocks the IO thread, it runs the guest in guest mode, it unlocks the IO thread when this returns for any reason, and we continue. The important thing here, if you can think about that, this is not threads. You just see, the only thing that can happen at the same time is the select and running in guest mode. The rest of the things are running as if they were only one thread. This is a good trick. The only part that is bad is we are not using all the threads all the BCPUs that we have continuously. Well, that IO thread, what does? Apart of doing this big select. Okay, it do for each select, for each file descriptor, It reads if it needs to read something, it writes if it is reading to write, and then it does something else. What is this important? This is what is called each IO handler. This is supposed to be fast, any of this. But to make things interesting, this thing that we were doing locking and the thing like that is that coding QEMU suppose that between this FD read and F write and the timer before, they are run in an atomic way. That means that moving to threads is very difficult because one of the things that we wanted to do for migration is move it inside that FD write, just drop the IO thread. That don't work. It's interesting. Well, and how this works at all? In general, this will not work because we have several threads, but they are waiting for one for a lock. Well, basically, we try very, very hard that IO handlers runs very fast. So that is not a problem. vCPU threads, normally they are running in guest mode, not in exit mode. If we exit a lot of times, we are doing something wrong. And when everything else, we cheat. What? The block layer. We call it unseek IO, but basically it is we move the operation to another place. Why? Because the IO thread is, otherwise we will install the IO thread. Network, we cheat still more. We do it in the kernel with vhost. Migration, we don't cheat, and it shows. Because we got the stalls. So, we don't cheat. Well, to make things more interesting, we have this nice abstraction that is buffer file. If you think about it, we have one abstraction that is buffer file to write in one file in uppercase. That was supposed to be buffered IO. You see, this is interesting. Why? Because if you remember our model with IO read and write, each time that we call, we cannot stop in the middle of one of these operations. So we have this unbuffered file with a buffer that can grow to not having to stop in the middle of one operation. Well, this is really interesting. So when we want to write something, we just write to this buffered file. This buffered file, we write it to one file. This file, we write it to one file description in that thing that we show, and the kernel do some more buffering. And then people wonder, why is that we are not able to saturate 110 gigabit network? I don't know, really. Well, it's enough buffering for you. This is some of the things that we have to do. Well, we are still better than that. That is measurement. What is that? This is QEMU. Everybody knows how things work. But for migration, we are better, and we have configuration. Just to know, so don't worry about that. One is migrate speed. Migrate speed, well, we start badly. Migrate speed is measured in megabytes. This is the same that my car runs at 5 kilometers. We start badly. Well, we will talk about this more later. And then mass downtime, unless this unit has the right units. That's in milliseconds. You know, this is one improvement. And then we try to make sense of them. We don't know. We do it wrongly, but we try. Something that we moved last year is that until now, migration always finished until last year. That means that if there were any problem, we spent a lot of time migrating, and we just forget this mass downtime was a hint. You know, if mass downtime was 30 milliseconds, with a big enough guess, we take 30 minutes. Well, it just happens, bad luck. As we migrate on speed, you remember that buffered file, and this is related with that. Remember that we have we measure speed in megabytes, and you remember that we have this IO handler thing that we were talking about. Okay, the IO handler for migration is something like that. While the number of bytes sent is smaller than mass speed, we send another page. So you can see now why. If we set the mass speed to 2 gigabytes, because you know we have a really, really nice network. Okay, we install the EO thread and the vCPUs while we send 2 gigabytes. And 2 gigabytes take a while to send. Yes, this is our architecture. You see that when we are sending, we are not testing for mass downtime at all, because why? It was just a hint. This is one of the problems. And the other thing is that, if you remember what I told about mass speed, we are measuring basically, it's not exactly true, but it's not exactly false, how fast we are able to write in one file in one file star. With that number, we extrapolate at how fast the networking goes. Now you know why our calculations are completely wrong. Well, to make things still more interesting, we have a nice optimization. That is, if we have one blank page, we just send 1 byte. We send the whole page. And you say, oh, that is nice. The only problem is that, if you see, we have a nice number of bytes sent minus the mass speed. If we send 1 byte instead of 4,000 bytes, we are doing that loop 4,000 times more. And you say, but we never have so many blank pages. Yes, you have. Why? Because if we have one in a big guest, think about it, 64 gigabytes of RAM, and we decide we want to migrate, we are going to balloon this thing, or we are going to stop it. Okay, we have a lot of pages of free pages. And that means that we stop. When you see that soft CPU interrupt that it happens on Linux, code is there. So you see that we are going well. Incoming migration, that is indeed better. As the buffer file was not good enough for our abstraction, when we have incoming migration, we don't have anything else. In particular, we don't have the monitor. We can do nothing. That is a quite interesting problem. But to be more libvirt can do anything. Indeed, we want to cancel the incoming side of the migration because something got wrong. Kill-9 is a really nice interface. And we have to configure everything from the command line, because we don't have command line, we don't have bottom half, we don't have anything. Well, that is basically how the states are. You can see that we are in a very good state. What are we going to do? Okay, this is one of the things that is to blame me, not nobody else. I told last year that I was going to finish being state. I didn't. So I did another things. There are several things that we are missing, but I finished several. For the things that are missing is basically Virt.io. The big problem is one list of requests that is very difficult to represent a list in a nice way that is easy to do. And the other thing is several mixed devices that basically we are going to have to change, because there are big fields and difference and other really nasty things. Subsection worked very well, except for a little thing. That is, to detect if we are in a subsection, we look at the first byte. If the first byte after the subsection happens to be the same value that the start of one subsection, we got it wrong. This is the thing that being state was not nice enough. It only have look ahead of 1 byte. It needs to have look ahead of n bytes.
I don't think the problem is look ahead. The migration format shouldn't be ambiguous in the first place.
But the migration format is there. It's the same that TCP should be perfect. But you know, that was done 20 years ago. But the format of migration was done 3 years ago, or 10 years, or 4 years ago, and we need to be compatible. We did it wrong. When we did the subsections, the idea is that they were going to be always at the end of other section. And we put it in the middle. Okay, we file it. Well, we can improve a bit there. That is, we can look at the headers, but then we need to do the equivalent of and get C or something like that between two packets. That is not nice, but it's possible to do. Migration thread, okay, UMS has been working there, and this fix a lot of our problems in the moment that we move to a thread. Why? Because the styles of the vCPU IO handler, if we are not doing migration in the vCPU or in the IO handler, obviously we can install them. This is one of the things that we improved. But the other thing that we can do is buffer a file, we can delete it. That is really, really nice. And other thing is that we can do better measures, because once that we are there, we are sending things for one page.
Why can we delete buffer file with a migration thread?
What?
Why do we get to delete buffer file by having a migration thread?
Because if we have one migration thread, we write from the migration thread. And we can do blocking or whatever, we don't care.
But I don't think we would serialize the devices in the migration thread.
Yes, why not? When we serialize the device, we are in stage 3. And in stage 3, QM will stop it. We don't care. At that state, we don't care, really. It is something like 2 milliseconds. Who cares about that? 2 milliseconds that we have the guest stop it. It's the same. And the other thing is that we should be perhaps able to saturate the network, because once that we have removed all the copies, it's possible. It's not easy to saturate high-speed networking, but if you have to do a lot of copies, it's impossible. The problem just now is how are we going to handle the dirty bitmap, because the dirty bitmap is used for several things. One is migration. That is easy because we need it. The other is VGA. I think that we are doing it wrong for VGA today, but it's not clear. And the other is TCG. TCG, nobody understands it, unless me. Okay, and incoming migration, we can move it in the incoming side. Once that we move it to a thread, basically incoming migration and outgoing migration are equivalent. If we move one of them to one thread, we can do the same with the other. In the moment that we do that, we can get one monitor or back. That means we can do the same. And we can do another thing that we can do now, that is start incoming migration in the middle of the monitor. Until now, we have to start migration before we do anything else. That gives same problems. Well, that is something. The dirty bitmap. The dirty bitmap is one of these things that is very, very efficient. We have 8 bits for each page. We only use 3. So only moving that to 3 bitmap, we got a 70% size reduction. That is quite nice. But we can do indeed better. That is how this thing works. Basically, we have two producers of dirty pages, KVM and MMIU. Forget about TCG, that I don't understand it. It's different. We can handle it the same way. And who consumes dirty pages? Who needs to know if some page has changed? VGA, code, that is TCG, and migration. Basically, this is everything that we have. And just now, we only have one bitmap. So what can do this to improve things? Well, we add ABI to the mail, we check well, and we got one idea. And that is, if we have several producers and we have several consumers, we get one bitmap for each producer and one bitmap for each consumer. And we sync them at some point. As you see, that is basically thread safe by design. The only problem is when we need to sync them. That is quite a good idea. I started doing something in that sense, and it's improved. Well, the bitmap is indeed better, the size reduction, that is. We have a really, really nice list of RAM blocks. But the dirty bitmap was not so nice to do one dirty bitmap in each RAM block. We have one dirty bitmap for all the allocated memory. If you think about that, if you have 1 gigabyte guest, you have memory in the 1 gigabyte, the first gigabyte, and in the 3 gigabytes because we put the VGI there. So we have a really big bitmap that is not needed for anything. But to fix that, we need to change the TCG. That is the only thing. The other thing I have basically in my moves how to fix that. Migration protocol format. This is basically one of the things of QEMU that is one of the ugliest things. Basically, we have one nice format that haven't learned from Fortran 60. It's one of the things that is not context-free grammar. Basically, we don't have one begin or end to mark where one section lasts. We don't have one size either. That means that we need exactly the same being state described. Only QEMU is able to inspect one migration image. That is really nice. And other thing is that once that we change the format, we need to do something like adding one checksum, because CPU is cheap. So to be sure that we haven't broken anything. Backward migration, well, we have talked about that in the QDev thing. The problem with backward migration is that we expect that migration do magic. This is really nice. When we try to migrate to one old machine, we start, for instance, machine with PC 014 when we are running in a version 015. Okay, that is just a lie. We are running the devices that were in 014, more or less, but with the features of 015. If you think about that, that is the equivalent that we are not doing PC 014 at all. Well, we expect the migration to do that. Basically, the fix to do that is to have every device need to be codified, and each time that we add one feature, we need to have one property to be able to disable this feature. And in the machine, we need to do something about that. Otherwise, this is no way to fix that. If we have that is not related with migration, migration can use it. Okay. Some solutions and some problems that happens here. One was the change of the migration format. One of the things that everybody wants to know is change the migration format to ASM1, XML. Well, nobody wants, but it's a possibility. But what happens? Basically, we don't care. Changing the format is the really easy thing to do. Why? Because, surprise, being a state is basically one visitor. We just have one description of how many states we have, and just now we do something like this to write one in 32. QEMU put SB32S with that value. If we will look some kind of XML, will be to count the functions or something like that, and we are done. If we want to do in any other format, we don't care. It's basically changed for every type that we have there. We need to re-encode in any other format. I mean, we don't care about that. It's just going, if we need to change the format, other thing is the headers of the format, something like that, but changing is really easy. The problem is that we are going to do with the problem that we have, not to change that. Other of the thing is that Anthony is really unhappy about what we have if one device gets split in two devices. Hint for everybody, Virt.io are PCI devices that shouldn't be. Okay, we have this device that is all the state. I have two fields, foo and bar. And we create another two devices, foo and bar. Okay, these are very simple devices because otherwise will not fit in the site. And the problem is that we have that state that we want to be able to migrate from the old state to the new one. Well, we can do that today. For instance, that way, we are going to do that only for foo, but bar will be the same. We got that old state in foo, in far, and we added one pointer to the new device state. And we have the new device state, it's exactly the same. And we do that, exactly that, nothing else. We create one being state description, exactly the same that we have before, and we have in the post-load section s foo equal s foo. We are done. Probably we need to do something else, like reload, something like that, but we are done. And the other way is changing the pointers, and we are done. Other thing that we need to think about that is post-copy. We are doing pre-copy. Pre-copy has a lot of advantages. One of them is that we always have all the state in one of the two machines. That means that if the network gets broken or something like that, we can always continue. The problem with migration just now is that memory and CPU versus network. CPU and RAM are growing this way. Networking is growing this way. If we have problems now, in 2 or 3 years, our problems are only going to be worse. What is the problem now? The problem now is that we are in a loop, if you remember before, searching for dirty pages. 5 minutes, okay. It's 2 or 3 slides. If we are moving to, if we are sending RAM, we want to have one downtime in the order of several milliseconds, 30, 100, something like that. The problem is that in 100 milliseconds, the number of states that we can send is really limited. Something like 9 megabytes with today gigabit, or something like that. If you think about that, if you have one guest that has 16 vCPUs and 64 gigabytes of RAM, it has never ever going to have only 9 megabytes of memory only. So the advantage of post-copy is that we copy the data to the other side. But what are the problems? Well, the problem is that we have half of the state in one side and half of the state in the other side. And the performance becomes undeterministic. Because when we have one page fault, it's possible that the fault is in the other machine. It's going to be slower than being there. It's not that I am really, really happy with post-copy, but this is something that we need to consider because we have problems with that. Conclusions. We in state, we have the same I have the same to-do list for next year. On with protocol, okay, we need to change that. But once that we change the protocol, we need to change all the problems that we have in being state. If we are not going to be compatible, things like we have with all versions and things that are wrong, like we are sending one field with a value that is not, we need to change that. And that is, we need to do that and the same problem at the same time. Migration threat, okay. UMS code is really, really nice start, and we need to do something like that. Bitmap handling, we need to do something more reasonable. Measurements. This is other thing that we fail, but really, really fail, because when we are not able to, when migration don't converge, we don't know if it is for a little bit or if it is for a lot. It's not, we need something like, guys is dirty memory at 300 megabytes by second, and we are only able to write to the network to 30 megabytes. Or we are 30, 31. I mean, if you try something, probably it will converge. We don't know just now. Post-copy, we need to study what to do there. Well, and basically that is the state from a point of view of migration today. You see that we have a lot of things to do.